In this video, I want to describe how to take nth roots of complex numbers, like square roots, cube roots, and so on. In some sense, it's more difficult than traditional real nth roots, but actually, it kind of gives you a new insight into the real nth roots as well. So it's kind of beautiful in a way, more powerful, and it has a very important lesson about complex functions. So pay attention to this one. Let's get started. Okay, so let's talk about what nth root is. So if W is a complex number, nth root over W is a complex number Z such that if you raise that number Z to the nth power, you get the W. Okay, so no surprise, I hope, there. We will see that unlike real nth roots, there's always n distinct nth roots, as long as you're starting with non-zero number. If you start with a 0, then nth root of 0 is always 0. But if you use a non-zero number, there's always n different answers to that. This is different from real nth roots, right? Like when you take a square root of like a positive number, for example, you usually get plus or minus that number. So you'll get two different types of square roots. If you're taking odd number roots, like a cube root, then you usually only end up with one of them. And when you're working with a negative number, the square roots and even number root do not work at all. But odd number roots, like a cube root, you could take the negative of that, right? So there's different rules for the parity of the n. It behaves differently between even and odd. But with complex numbers, you could always do it. And you know exactly how many we have. Okay. To do this, we're gonna need to use the polar form. So let's say W is the number that we want to take the nth root of, and Z is the nth root of W. Okay, so Z to the nth power should be equal to W. Let's write that down in the formula. It's easy to raise powers in polar form, so that's why we're using it. So Z to the n is going to be R to the n, which this is the modulus, and e to the im theta, and that's going to be the argument. And we want this to be equal to W, and W is rho e to the I phi. Okay. So looking at the polar form, we know exactly what equation we have to satisfy. So the modulus has to match, right? So R to the n should be equal to the rho. And the angles, I mean, they have to match as well. But the thing about angle is that they could be off by any multiples of 2 pi, right? Because angle wraps around and there's multiple angles that are a match, right? So e to the im theta should be equal to e to the I phi, okay? So this means that the modulus part we can compute. R should be nth root of rho. So now we are describing how to take nth roots, but taking the nth root of a positive real number, we already know how to do that. So this is the nth real root, positive real root of rho. Okay. So modulus is given, that's fixed. Now let's look at the angles. So we know that n theta should match phi, or it could be off by 2 pi times some integer, because that registers as the same angle. And then if you divide both sides by n, this is what we get for the argument for the root. So we take the phi, so the original angle for w, divide that by n, and then you add some multiple of 2 pi over n. Okay, and k could be anything, right? K could be 0, it could be 1, it could be 2, and so on. So there's lots of different answers here. But the thing about it is, as you increase the k, eventually, so when k is equal to n, then the n will cancel out and you'll get 2 pi. So you kind of get back to the original angle. So if you're counting for like how many different angles are there, the k could be from 0 to n minus 1, and after that it's going to be repeats. So there's n different angles that would work here. I hope that made sense. Okay, so I want to kind of draw what the nth roots look like, right? So the modulus is fixed at nth root of rho. So that's rho to the 1 over nth power. And the different angles, they are all separated by 2 pi divided by n, right? So for example, if I'm taking the fifth root, I take 2 pi, that's a full revolution, and divide that equally into 5 pieces, right? So if I kind of imagine 5 different points with equal division of angles, so these are 5 different answers equally spread out around the circle of radius rho of 1 over n. So they all sit in the same circle, and then they're kind of equally spread apart. So yeah, I guess if this in angle, like in degree angles, 360 divided by 5, so I think that's 72 degrees apart. Okay, and this is true for any nth roots, right? So if it's cube root, there'll be 120 degrees apart, right? Like exactly 360 divided by 3, or 2 pi divided by 3 radians. Okay, so let's do an example of taking the 3 cube roots of the complex number 8i. So the first task is to write it in a polar form. So that's actually not too hard here. The modulus is 8 because it's 8 units upward. And if I'm going exactly upward, the angle, the argument is going to be 90 degrees or pi over 2 radians. That's what I have up here. Okay, so let's take the cube root. So first I take the cube root of 8. The cube root of 8 is 2. Okay, and I also take the angle and divide that by 3. So pi over 2 divided by 3 is pi over 6. Okay, so that's one answer. But I could get 2 other answers because there's 3 total answers for cube roots. And I can get different answers by adding 2 pi over 3, and then 2 times that. So if I add 4 pi over 3, I would get another answer. And if I try to add 6 pi over 3, I get back to the original pi over 6 answer. So I'm not getting anything new at that point. Okay. So this is the answer in polar form. So I can add the angles together. And if I want this to write it out in standard form, like a plus bi form, I could use Euler's formula. So instead of writing e to the pi over 6i, I replace that with cosine of pi over 6 plus I sine of pi over 6. And pi over 6 is 30 degrees. It's a nice angle. So if you remember that, we could write down the exact answer. So cosine of 30 degrees is root 3 over 2, and sine of pi over 6 is 1/2. So this is what we get. And this happens to simplify. And here's what we get for the three possible roots for 8i. Okay. If I graph it in the complex plane, that's what it looks like. That's the 8i here. This is a circle of radius 2. And there's like 3 angles here that are equally spread apart. The bottom one is exactly imaginary on the negative imaginary axis. Okay. And so this is the process. We walk through how to take nth roots. So this was a cube root example. If you start with a number, alpha plus beta I, you first convert to polar form. So I have to take the modulus. Then I can write down the list of solutions by taking the nth root of the modulus and looking at different angles equally apart by 2 pi over n. And then finally use Euler's formula to get them back into the standard form. Okay. Nth roots of 1 has a special name. It's called nth roots of unity. So this is all on the unit circle. 1 is always nth root of unity because 1 to the nth power is always equal to 1. And then the other ones are equally spread apart, right? So if I'm taking, for example, 8th root of unity, then I'll get 8 different roots of unity equally, like they're all 45 degrees or pi over 4 radians apart. Okay. All right. And this solution of like taking equally angle apart kind of gives you an insight into why there was a weird rule in the real roots. You could see that if you were taking even numbered roots over real number, then there's 2 answers that lie on the real axis. And if you're doing odd roots of entity, then only the positive root will be on the real line, and so on. So if you just look at what roots are on the real line, like that's what gave you the weird. This you can sometimes take cube roots or square roots, and sometimes you get multiple answers. But if you see the whole picture from the complex point of view, you could see exactly why. I hope that made sense. I think it's more powerful and beautiful from this picture, from this point of view. Okay. And this kind of touches at one of the things that we'll have to frequently work with. Nth root of taking the nth root is a multi-valued function, right? There's multiple valid answers to this question. So you have to be more specific usually when you take the square roots or cube roots of something in complex world. you have to specify which one you're taking, right? So in the previous example, there were 3 equally valid answers. So you can't just say, look at the cube root of 8i. You have to pick one. And one thing you could do is you could always say, give me the one that comes from the principal branch. So that's the answer you get, where the angle is angle comes from where the original angle was between pi and negative pi, right? So you can kind of look at that this first answer here and say that's the answer I'm looking for, if you wanted to specify by saying the principal branch. But if you want to look at the other roots instead, like negative root 3 plus I is equally valid answer, or negative 2i, maybe that one's simpler looking, so maybe you care about that one. Then you have to specify, hey, it's the root that gives you negative 2i, right? So you have to be a little bit more specific if you don't want to talk about multiple values at once. Okay, so if you want to focus on one particular branch, we need to specify the value given at a specific point. Okay, I just kind of use the word branch, but that's what we use if you want to pick out one particular function out of this multi-valued function. Okay, and we've actually already encountered this. We looked at Cardano's formula for solving cubic polynomials, and we're taking the cube roots. And sometimes the inside is complex, so you already have to do the cube roots of complex numbers, right? You might wonder, which branch should we look at? Well, you can pick one, and it works. And then if you want the other solutions, you have to pick different branches, right? Okay, here's where I want to end the video for the roots. I will see you later.